Hi everyone, my name is Mathilde, I am from Cybersecurity, and I am very happy to be here and to welcome you to our talk, Taking the Quantum Leap with Go. So, during this talk, we're going to present a library that implements post-quantum cryptography. And just a bit of background before we start, this library was developed as part of my master's thesis, so this is technically a joint contribution between Cybersecurity and my university EPFL. So about me, I enjoy working with all kinds of cryptography, and especially to apply them towards privacy-enhancing technologies. I will now let my co-speaker Yolan introduce himself.
Thank you, Mathilde, and hello everyone. So my name is Yolan Romailler, and I'm a cryptographer. This was done while I was at Cybersecurity, mostly delving into digital signature schemes, fault attacks, side channel attacks, and also consensus algorithms, blockchain, and sometimes security engineering. I'm currently working at SICPA on the future of digital currencies and identity. So at Cybersecurity, I was part of the research team with Mathilde, and the research team is very interested into staying on top of things, especially bleeding edge tech, such as post-quantum cryptography. So you might be asking, what is a quantum computer in the first place? A quantum computer is a new kind of computers that is able to leverage quantum mechanisms to run quantum algorithms, which are quite different from the algorithms we are used to run on our classical computers. And the big problem we have as cryptographers with quantum computers is that they are a huge threat to public key cryptography. Basically, all of the schemes we are using nowadays are broken by quantum computers, at least in the public key cryptography space. This is not true for symmetric key cryptography and hash functions, which are somewhat impacted but not completely broken. So you might be asking, why do we need to care about public key crypto? And public key crypto is actually used everywhere nowadays. From TLS to SSH, when you connect to a VPN, if you encrypt your passwords using GoPass, all of these are based on public key crypto under the hood. And post-quantum cryptography is a new field trying to find quantum-resistant algorithms. That is, new public key schemes which resist to the quantum computers algorithms that we currently know. And there are a lot of different kind of quantum resistant or post-quantum cryptography schemes. Some of them have like very large payloads, such as hash-based crypto. Some of them are fast but have somewhat larger messages than what we currently have, for example, lattice-based schemes and so on. So we needed to study and really try and define what are the best algorithms. And to do so, the NIST launched a post-quantum cryptography competition in 2017, 4 years ago, to try and define the new standard for post-quantum public key cryptography. And currently, we're still in the research and standardization phase. So far, so good. And once we have this new standard, which is 1 or 2 years afar, we will need to deploy it. And as soon as we've deployed it, we are safe. We don't care about quantum computers. But the problem is we don't know how long it will take until a quantum computer that is big enough to break nowadays schemes will be built. But as soon as such a quantum computers exist, then we are doomed because all of the internet as we know it scrambles. And you might be remembering about the SHA-1 problem we had in 2017. SHA-1 is known to be weaker than expected since 2005. And it took 12 years until 2017 before an actual collision was found and SHA-1 was considered completely broken. But that meant that we needed to migrate away from SHA-1. And from 2005 until 2017, not much was done. And in 2017, everybody realized, oh, we need to migrate away, and they started to do so. But sadly, the collision was already there, and if you take, for example, SVN, it was broken by collision in a unit test for WebKit. Or if you take Git, for example, all of Git is based on SHA-1. And if you have an old repo using SHA-1, there is no easy way to migrate to using SHA-256. So if you create a new repo now, you can use SHA-256 and you're fine. But if you have an old repo, then it's a bit complicated. And that's a bit sad because we really need crypto agility. That is a way to switch easily cryptographic algorithms when new attacks are found or when they are broken. Currently, there are not so many quantum computers and they are very small, so they are not a threat for public key crypto at all. And you can try them online. So IBM has a quantum computer which you can try online. It has a few qubits, so you can't do much with it, but it's freely available. In a few years, 5, 10, who knows, we might have thousands of qubits inside of cloud computers readily available for anyone to try and break RSA or EdDSA, which would be a huge problem if we haven't moved away from these vulnerable algorithms by then. So, as you've seen, cryptography agility or crypto agility is a true challenge, and we need to address it as soon as possible, because you cannot just say, okay, I double the key sizes just like for symmetric key crypto. No, if you want to have a RSA which is quantum resistant, you would need 1 terabyte keys, and that won't fit on a smart card for sure. So now for a few crypto refreshers. So maybe you already heard of hybrid encryption. And that's basically when you use public key crypto, which is super slow, to establish a common secret, which is then used as a symmetric key to encrypt the data, because symmetric key crypto is super fast. And since everybody wants a fast internet and fast protocols, fast connections, it's way better to use as little public key crypto as possible and to use, for example, AES as a symmetric key algorithms to encrypt data, because AES is only a few cycles on most CPUs nowadays. So most of the protocols you know and use are based on the so-called hybrid encryption, using public key crypto to establish a common key and then using symmetric key crypto to communicate. And now I will let Mathilde explain you a bit more about DSA and CAMs.
Thank you. So, as Yolan explained, public key cryptography is indeed slower than symmetric key techniques regarding encryption, but yet very much needed in our online world to obtain different protocols with different security properties. And today we will talk about 2 of those public key protocols. First, let's start with the DSA. The DSA, digital signature algorithm, is used to produce a signature on a message using a secret signing key. The signature can be verified by anyone holding the verification key, which is openly disclosed. A secure DSA has the unforgeability property, meaning that it is very hard, like impossible, to create a valid signature without actually knowing the secret signing key associated to the publicly disclosed verification key. And in that case, the DSA can be used as an authentication mechanism because a valid signature is the proof that the signer indeed knows the secret signing key. The second protocol we're interested in is the key encapsulation mechanism, shortened to KM. The goal of a KM is to securely transmit some key material over an insecure channel. This key material is most of the time a symmetric key material, and as you understood, key encapsulation mechanisms are very important because they are the first step of every hybrid encryption scheme and are necessary to transmit the symmetric key that will later on be used to open this secure tunnel and encrypt the actual data. In our library, we offer both a KM and a DSA. We chose to instantiate them with the Crystal Suite algorithms. meaning that our DSA follows dilithium's pseudocode and our KM follows Kyber's pseudocode. And we chose to work with Kyber and Crystal because both are very promising candidates for the post-quantum computers area. They are finalists of the NIST post-quantum cryptography standardization process, which strengthen our belief that they have like this good trade-off of like performance, security, and everything. For the technical details, they are lattice-based and stood out to us because of their very simple arithmetic structure, tight security proofs, and overall versatility. Regarding the performance, as we will see, they can even excel some of the classical solutions that are widespread. The main drawback of the Crystal suite is the relatively large output size. And when I say outputs, I mean like public key, signature, or ciphertext. I would like to nuance this a bit by saying that yes, it will impact the performance of your project and of your infrastructure, but it will never be like a bottleneck like a 1 terabyte RSA key could be. So our contribution really with the Crystal Go library is to port the reference implementation from C to Go. We make it open source and available at the following link, but we also added the QR code for faster access. As at GopherCon, our mission is really to provide code that is practically secure. We put a lot of efforts into integrating as many security features as possible. And we want this security process to be continuous and interactive. So we encourage you to challenge our code, open issues on our GitHub, or simply just engage in some kind of conversation. I will now quickly go through the API of our library and demonstrate how easy to understand and to use the Crystal Go library is. So the flow of Crystal, Kyber and Crystal dilithium is very similar. It works in two steps. First, the users have to agree on a security level that they want to use. And this will define all the parameters that are going to be used internally. And once the parameters are defined, then the core functions can be invoked. And when I say core functions, it's like generating the keys, signing message, and so on and so on. So our library has helper functions that can, for example, return the size of a signature of a public key and extra if you want to use fixed size arrays. I will not cover the helpers in this talk, and we refer to the README of the GitHub repo for a more exhaustive list of the possibilities offered by our library. So let's start with dilithium. So as I mentioned, these two steps really can be seen when looking at the API, because the API can be divided into two groups. So the first three functions on your left define a dilithium type. And a dilithium type is basically a choice of a security. So from top to bottom, you have an increasing security level, meaning that creating a dilithium 2 instance will provide the lightest security guarantees, whereas dilithium 5 provides very strong security. Then the core functions are these signature and verification functions. So the key generation will produce a verification key and a signature key. The signature function will take a signing key and a message and produce a signature that can be verified using the public key. So code-wise, what does it look like? So first step, the users have to agree and create a dilithium instance based on the security level they want to use. So for example, in here, they create a dilithium 2 instance. They can use this dilithium instance to invoke the core functions. So for example, the first user can generate a verification and signing key pair and disclose openly the public key. Later on, he can sign a message using his signing key, transmit it to the second user, who can verify it against the public key received earlier. So if the execution is honest and everything went fine, then the OK boolean returned by the verify function will be true. Similarly, for Kyber, you have the type and core functions. The type function defines the security level by creating a Kyber instance. So from top to bottom, you have an increasing level of security. The core function of the key encapsulation mechanisms are the key generation, the encapsulation, and the decapsulation functions. So the key generation function will produce a pair of public and private keys. The encapsulation will, given a public key, creates a shared secret and the encryption of the shared secret. The ciphertext can be sent to the private key holder to decapsulate so that they will recover the same shared secrets. So code-wise, similarly, let's repeat the process. First, we define the security level by creating a Kyber instance and invoke the KEM methods on the Kyber instance. So following the flow of a KEM, we first generate the keys, then encapsulate, and then decapsulate the shared secrets. So in our case, the value of SS will be the same for both users and can be used as symmetric key material to open a secure channel. Regarding the performance, the security of a library is theoretically guaranteed by the security proofs contained in the crystals paper. They are peer-reviewed and really challenged, so we're confident that our library is theoretically secure. Now we know that there exist some attacks that target algorithmically secure implementations. This is the case of side channel attacks. But what we did is that we thoroughly collected all the vulnerabilities and exploits present in the reference implementation and integrated countermeasures in our library. This is something that is not usually done, but we think that having side channel is really not a good thing. Regarding the performance, the runtime and size of outputs are reported in this table. So the numbers are for recommended security level, and the takeaway really is that the calling a function takes from a fraction of millisecond up to 2 milliseconds, whereas the size ranges from 1 megabyte to 3 megabytes. So we thought that this number might be a bit abstract to you, so what we did is that we compared them to the performance of the protocols that are contained in the Go's official crypto package. So we compared the RSA, OAP, and EDSA implementations against our Crystal Go implementations. And as you can see, the trade-off that I mentioned of great performance but large output size is really clear when looking at our benchmarks. So the runtime of our algorithms in blue is way lower than the classical solutions contained in the Go's crypto package, whereas the bandwidth that is necessary to run the algorithm is a bit bigger or orders of magnitude heavier than the classical solutions. Nevertheless, we demonstrate the practicality of our library by integrating it in the WireGuard protocol. And spoilers alert, we show that adding quantum resistance to the WireGuard protocol has an overhead of sending 2 extra IP packets per handshake, and regarding the runtime, it adds 0.2 milliseconds, which is totally practical. If you want to learn more about the process of how we integrated our library into the WireGuard protocol and added quantum resistance, we encourage you to attend our talk at the NIST Post-Quantum Cryptography Standardization Conference happening in a few days. To conclude with, we hope that the experimental results that we showed really should motivate you to start the transition towards post-quantum alternatives and to start integrating our library into your infrastructure. Moreover, if you're going to use some cryptography, we encourage you to use something that proposes and offers some practical security and countermeasures against side channel attacks.
All right, so that's basically it. We'll be back live in a few seconds for answering your questions. And if you want to check out our research blog, you can find there a few posts on the topic, including an explanation of how to use library with code examples. And here are a few links as well if you want to learn more on the topic. We'll be releasing the slides on our blog and also on Twitter, so if you need them to click the links, or if you want just some refresher for later, check them out. And with that, we are happy to answer all your questions.